first. So the problem overview is about learning to rank. So learning to rank is like a class of techniques that apply to supervised machine learning problem to solve the ranking problems. So what the ranking problem is, that if we give a query to a search engine, so we should get a list of documents and they should be in the order of the relevancy with the query. So yeah, so like if we give a query queue, we get a document one as a rank one, document two as a rank two, and among till document M. So yeah, and okay. So the difference between the LTR and the traditional supervised machine learning problem is that traditional machine learning problems tries to solve a prediction problem, right? That is for a classification or regression, and it's on a single instance at a time. When I give an email uh, to an algorithm, to a machine learning algorithm, it gives me either it's a spam mail or a not spam mail. So this kind of says that it gives a single numerical score for that instance. But the learning to rank problem is applied on a list of items. So the aim or the output of the LTR model should be a list of items rather than a single score for an item. Okay, so yeah, and one good point to note about it is that LTR focuses more about the relative ordering of the item rather than the exact score which each item gets. So PS the each item, I mean that each document. So yeah. Now there are different LTR training methodologies that are available. So the three ways that my LTR model can learn is first is the point-wise learning. So in this, I take one candidate. One candidate is just one document, and I compute the score between the candidate and the query, and it gives me the score. That's it. So then the pairwise learning methodologies. The pairwise learning methodology is that we can take a pair of candidates as input, and the model will tell which candidate is ranked higher. And the list-wise solving technology algorithm actually takes the entire list all at once and it gives optimizes its order. So you can see that it takes a single input and the pairwise takes two inputs and the list-wise takes a entire list at a time. So our Ranknet problem is solved by the pairwise learning methodology. Okay, so given this, let's start the Ranknet. So yeah, so the Ranknet has actually it consists of a neural model. So what's a neural model is we give a d-dimensional input and we get a single real value for it. For instance, let's say that if document X1 is ranked higher than document X2. So my model should output that f of X1 should be greater than f of X2. That is the value. So, okay. And we will see what is the d-dimensional vector means. So we kind of compute the d-dimensional vector for each of the document to represent it in some higher space. Okay. Now the output of the ranking model. So the output is, let's say, for a input xi, it gives an output oi for and yeah, and then we compute OIJ, which is the difference between those samples that we inputted. So xi, xj. So it's computed f of xi minus f of xj. So yeah, like these are just a mathematical representation. It will help us in the future.
Can I
Okay.
ask, can you give some examples of outputs of the model? So, um, the model itself is looking at only one of the, say, documents at a time, right? And is it returning a number between 0 and 1 or any number? How does that work?
So yeah, it's a real number. That's what I said. So we input a document at a time and we get a real value for it. And I think your doubt would be cleared in the next slides.
Okay.
Okay. So yeah, this is what I get output OI for the neural model f of xi. And yeah, after that we convert it to probabilities. So the probability definition is that for if the document xi is ranked higher than document xj. So we compute the probability pij for it. And let's say the target probability for this is, let's say, pij dash, which is which should be the exact value that we stored in our dataset. And yeah, we convert this using the sigmoid function, which is we take in Oij, which was the output of the neural model, and we apply the sigmoid on it, and we compute Pij through it. And the loss function that we use to compare this, the probability that we get and the target probability, is the binary cross entropy loss function, which is the standard formula of the binary cross entropy. So yeah, so this is how the workflow goes. So let's say we input a candidate 1 and we input the candidate 2, xi, xj. Both of them goes to a separate
Mhm.
neural network, and we get an output oi and oj. So these are actually the raw values right now that the neural model outputs. After that, we subtract this oi minus oj that we saw, and it gives me Oij, and we pass it through the sigmoid, which converts it to a probability between 0 to 1. So this is kind of a normalization that we apply here. And the output probability is then compared with the target probability using the loss function, and then we backpropagate the loss function. So one good point to note here is that these both of the networks have shared weights actually. So it's not like a separate pipeline. I draw them as two different boxes because just to explain what is happening inside. Okay, so yeah. After this, I think it's so Julian, your doubt is cleared with this.
Yep. Yes, thank you.
Yeah. Okay. And yeah, after this, yeah, the metric. So the metric that we use to judge how good is my final overall rank list is normalized discounted cumulative gain. So it's kind of like, it sounds complicated, but it isn't. It's really a simple metric. Okay, so the premise of DCG, the discounted cumulative gain, is that the highly relevant documents appearing lower in a search result should be penalized. Okay, so let's say we have to focus only on 2 points. Firstly, how relevant the document is. So this we call relevance, and what is the rank of that document. So okay, and this is what the penalization term consist of. And we also call it discount in the discounted cumulative gain. So let's say that we want to compute a DCG for a list. So the DCG for a list is this formula, that is 2 to the power of the relevancy score minus 1 divided by the log base 2 of the I plus 1. So I here is basically the rank of the document. So this denominator, it represents that what is the rank of the document, and the numerator represents how relevant is that document. So let's say if a document is ranked really low, if a relevant document is ranked really low in the list, so the gain that we get from that is really low because the denominator actually shoots up. So yeah, this is how the DCG is computed, and we add the score. We add this score for all the documents that we have in a list. And yeah, this relevancy score is actually the output of the the output of the model. This OI. This is the relevancy score, and it just tells us how relevant that document is. Okay, so this is how DCG is computed. And now, since like each of the search results vary in length, right? For let's say for a query, we have let's say 120 documents that are ranked. And then for another query, there are, let's say, 130 documents. Then for another query, let's say we get 100 documents. So to normalize that, such that we are able to compare the DCG score of different queries, what we do is a normalization, and the it normalization factor is computed using the ideal DCG. So what we do is we compute this DCG for the ideal ranked order of the list. So let's say that ideally what should be the rank of the list. We compute the DCG for that, and we divide it with the DCG that we got as the output of our model. And yeah, we normalize it and we call that NDCG. So the normalized discounted cumulative gain. So the gain is this term, and the discount is actually applied by the rank of the document, and cumulative is the, like we sum over all the documents of the list. So this is the summation, and yeah, this is normalized discounted cumulative gain. So this is the metric that we use to rank any that we use to compare any LTR algorithm. So yeah, so I actually trained the model on the MSLR Web 10K dataset. So this is the dataset that the paper actually uses. So what it has is this 10K refers to the number of queries that the document that the dataset has. So it consists of 10,000 queries, and in total there are 1.2 million query document pair. So we can say that for each query, on average, we have 120 documents. But yeah, it's an average. Actually, the as we saw, the documents per query changes from query to query. Okay. And then each document is actually represented by a 136 dimensional feature vector, which tells us about the content of the document. So the features that are extracted for the document are using the classical NLP metrics like term frequency and TF-IDF. And the size of the dataset is 1.2 GB. So yeah, the training setting that I use is the optimizer that they use is the Adam optimizer. The learning rate is 0.01. It's a standard learning rate, like nothing much in this. And they train it over 20 epochs. And yeah, they also use LR scheduler, which is step LR, step size of 10, and the reducing factor is 0.75. And yeah, the neural network that we talked about is consisting of two layers. So the first is we input the feature vectors that are 136 dimensional that we saw initially, and then it goes to a 64 dimensional layer, and finally a 16 dimensional layer, which gives a single dimensional output through. So yeah, so the activation that is used in between the layers is ReLU, and the last activation to compute the probability is the sigmoid that we saw earlier. Okay. And yeah, the MSLR is actually the data set is divided into five folds, and the fold one, five sets, and they have, like, for fold one, they have use set one, set two, set three as the training set. Validation set is set four, and test set is set five. And yeah, this is like I did the five-fold cross validation for this, and these are the results that I got. So yeah, they compute NDCG at different ranks. So it's NDCG at rank 10, NDCG at rank 15, and NDCG at rank 30. So like whenever I search something, I just want my optimum result to come up within, let's say, top 10, top 15 documents only. So that's why they compute it only on this 10, 15, and I computed it on 30 as well. So in the paper, they just computed it NDCG at rank 15. Okay, so these are the results, let's say, for five folds. You can see that it's not varying much over the five folds. And the overall results are 0.42 for NDCG at 10, 0.44 at NDCG at 15, and 0.49 at NDCG at 30. So if we see at NDCG 15, this is the result that they got from the paper, 0.5 plus minus 0.05, and we got 0.44 plus minus 0.13. So yeah, in the paper they got a better result, but actually they didn't reveal what are the training settings. So these are the training settings that I actually used, and yeah, maybe some more optimization and we can reach this 0.5 value. And I did two experiments. First is I tried to use SGD if that works, but that actually dropped my performance. So 0.40, 0.43, and 0.48, which is a decrement from the Adam optimizer that I showed previously. And lastly, yeah, I trained it for 10 epochs as well. And if you see, the result are just a little bit lower than the 20 epochs. So we can actually train it for only 10 epochs, and if let's say we have computational limitations, and yeah, it will give us the result, because actually the training time is 5 hours or 6 hours probably. So, if we do it for 10 epochs, we will be done in just 1.5 hour only. So yeah, these are the results, and yeah, thank you. So any questions that you didn't understand?
Aryan, for the final runtime, for the like creating the ordering, for like any abstract ordering, it's just linear, right? Is what I took away.
I'm sorry, I didn't understand.
Like once I have Ranknet trained, to then take like a list of like say 10 documents and order them, the runtime is just something is O of 10 essentially.
No, no, no. So the inference
Or you
time,
need it pairwise.
yes, I think you are asking the inference time on the trained
Mhm.
model.
Yeah, yeah.
Yeah, yeah, yeah. It's quite late. It just gives the result. Let's say if you want to rank just 10 documents, it will give you in seconds.
Hmm.
Even the inference time, it's just let's say 10-15 minutes on
Hmm.
a document list.
So I'll ask a framing question, which we may not have the answer to yet, but
Mhm.
can you go back to the slide with point-wise, pairwise, and list-wise?
Yeah.
Just so, do we have any insights yet into um, the trade-offs between these three different approaches?
So the insight is that the point wise is actually really easy to train, because you just input one candidate. The pairwise is more computationally expensive, and the listwise is exponentially computationally expensive, because you take in the entire list at a time. But if you see results, so yeah, the listwise LTR training methodologies actually gives us the best result, because it takes in input the entire list. So like if the model is able to see all of the data at once, so it is able to rank it better. It's the same with what happens with attention. If you get a whole set of documents, you will be able to rank them in a better way.
Yeah.
Yeah. And the pairwise actually has that limitation. That's why the listwise came into the picture. So yeah, like this is what I have on a very abstract level. I don't know the details about that.
Yeah. This is I think, the first in a six-part series of learning to rank models. So
Uh-huh.
yeah, you did a great job of
Yeah,
that.
so maybe next time we can do the list twice.
Addison's busy inventing new list-wise algorithms. Cool. Any other questions? You can give it a moment.
I think this is a follow-up. Sorry, this is a clarification question. For two pairs of document, you do one backpropagation.
Yeah.
Uh,
Yeah, I take in two documents, I do the back propagation. So if you see here, in the pair, in a point wise, only a single document would go in. In a
Mhm.
pair wise, two documents are going in, and in a list wise, all the documents would go in, and we just have to do only we just have to do the forward propagation and backward propagation only once. Like not only once, but um, what you say, like in this, we have to
mhm.
do forward prop and back prop for all the pairs of the documents that are there. But for list-wise, that would not be required.
Yeah. Uh, let's say I'm deploying this model into production today,
Hmm.
and I have to rank 10 documents. So idea is I give the entire document as I input to the model, it gives me a score. And for each document, I have a score now. So for a given query, I just like sort the documents by the score which I've obtained for the model. Is that the final ranking?
Yeah, kind of, but that's the ranking for point wise. That what you said. It
Okay.
actually, yeah, this RankNet, it doesn't depend on the score. What it does is it first, let's say that model rank one, the candidate one is ranked higher than candidate two, so it will do
Mhm.
rank them. Then it will bring in candidate three and compare it with candidate one. Bring candidate four, compare it with candidate one, and it sort of computes that, if you can imagine the matrix. Uh,
Hmm.
yeah, yeah, yeah. And then using that matrix, it ranks.
Okay. Cool. Thanks.
Yeah.
Is it fair to consider this model a form of contrastive learning? That might be kind of a self-evident statement, or maybe someone disagrees.
Uh, yeah, I don't have much idea about contrastive learning.
Oh, it's as you see, we're basically training. If we want OI to be higher than OJ, then we're basically training the model to rank it higher, and kind of push them away.
Yeah, 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 yeah.
Yeah. Cool.
Yeah, we actually kind of don't need the labels. Yeah, but for back propagation, we need the labels. I think in contrastive learning is a self-supervised learning technique, right?
Oh, that's a good point. Yes.
Yeah. But yeah, but we can use a trained model to then do the contrastive learn. Yeah, but no, that would be inference.
Yeah, you do need labels, I think, which is kind of what we were just talking about.
It was pretty fair. Like it was a pretty easy algorithm. It was in what, published in I think 2004 or 2005.
Yeah. Which all, subsequent learning training algorithms are based on to some extent. So,
Uh-huh.
okay. Any further questions? Okay. If not, then yeah, fantastic job, Aryan. And I hope everyone can, participates in our learning to rank series here as
Uh,
we go through those various learning to rank and pairwise and listwise algorithms.
uh-huh. Yeah. Thank you. Thank you. Happy to present.
Awesome. Great presentation. Thanks.
Yep.
Thank you. Thank you so much.
Thanks, guys. Have a really great day.
Yep.
Good job, Aryan. Yeah, thank you, everyone.
Thank you. Thank you.
Thanks. Bye.
All right.